recording. Okay. Okay, so today we must move on and we must try to build. So the aim of today is to build a generic tensor on the vector space VB. So this is what we want to do. The tensor T will be n times, so I must be very careful, so maybe I invent another symbol, m times contravariant and L times covariant. Okay, so this is what we need to do today, and we will try to do this very, very slowly. Before we do this, I tell you something. We invented, starting from the vector space VB, the dual V star B. Okay? So, somebody could say, okay, in a similar way, I could invent V double star B. V n times star B. So I could build the dual of the dual of the dual. I could do duality one after the other many times. Actually, what we can prove is that the double dual is equal via, it is not exactly equal, via an isomorphism I don't remember exactly if there is a wire or not there. Why an isomorphism? There is an identification between the two sets. The isomorphism means that the structure is the same. In this case, because iso means in Greek the same, and morphism, morphe in Greek means the shape, the form. Okay. So there is the same form of the two vector spaces. Okay. And in order to understand what we are doing, and in order to make our reasonings well grounded, I think it is very important to understand how this isomorphism is built. Okay. So we should consider L star in V star star B. And what is doing this L star? It is mapping an element in V star B into a real number. Okay. So this is this is the way in which we are building always the dual of a vector space. So please, there is nothing strange in what we're doing. For every vector space, we can build its dual with all linear maps into R. V star B is a vector space. Therefore, we can always consider V star star B. So there is nothing strange in this. We already said that the dimension of VB is equal to the dimension of V star B. This we have proven. Okay. This we have proven in the previous lectures. I remind you how we did it. We introduced the basis E upper I of V is equal VI. Okay. And we have proven that E upper I is a basis for V star B. Okay. So having proven this, we have proven that the dimension of VB is equal to the dimension of V star B. Okay. So this is crucial in what we are doing, building when you construct the dual, the dimension remains the same. Okay. So obviously, dimension of VB equal dimension of V star B equal dimension of V star star B. So building a dual is not increasing the dimension of the space. Of course, we are dealing with finite dimensional vector spaces. Okay. In the case of infinite dimensional vector spaces, the situation is much more complicated than this. But for the moment, we are ignoring this. Okay. Now, I consider the following phi, which is a map from VB into V star star B. Or if you like, I map a vector V in VB into a vector phi of V belonging to V star star B. So L star, an element of V star star B, is built in this way. Okay, maybe I am running too much. So I start considering phi of V, an element of V star star B, as follows. Phi of V, what is phi of V? Is a linear map on the set of elements of V star B. Okay, so phi star V, phi V applied to L must be a real number. So this symbol here means take phi V and calculate its image on L. Okay, and now this real number I calculate this way, L of V. So this is now fixed and L is variable. Okay. Now it is obvious that phi V calculated in alpha L plus L1 plus beta L2, which by definition is equal. So this is a definition on this side. What I have written on the left side is defined in with what is written on the right side in this case. Okay. So what is this? By definition, this is alpha L1 plus beta L2 applied to V. This is by definition of linear combination of elements in the dual space. It is alpha L1V plus beta L2V. Okay. And finally, we have that this is alpha phi V of L plus beta L1 plus beta FV L2. Okay. And so we have proven that phi V belongs to V star star B. Okay. Okay. So phi of EI is a set of linear independent vectors. Let us prove this. This is very easy. So I can write alpha I phi EI equal 0. Okay. So alpha I phi EI applied to V is equal to 0 for every L. for every L belonging in V star B. Okay. By definition, again, we have that alpha I L E I is equal to 0 for every L. Okay. And we can apply, okay, what is this? Let us be careful. This is a linear combination of this 0 is an element of V star B. This is the 0 in V star B, and this is a linear combination of elements of V star B. Okay? So in order to conclude our reasoning, we must say that for every L and for every V, alpha I, L, E I applied to V is equal to 0. And now this 0 is what? This 0 is a real number. Okay? Because I am applying a linear map in V star B to a vector in VB, so I get a real number. Okay? Okay. You know, I told you several times that the upper and lower index is a very effective way for discovering mistakes. Now, I said something wrong, but I immediately can understand why I'm wrong, because I was doubting what I was telling to you since the very beginning. And now I have the certainty that I was wrong, because EI at the top is a covector. Okay, so let us learn by my mistakes, because it is impossible that somebody is right all the time, and a good notation is indicating the best way for avoiding mistakes and possibly correcting them. EI lower, EI lower is an element of VB. Okay? And we are inventing a mapping phi from VB into V star star B. So I must have here a vector in VB. EI up is a covector. So everybody should jump on his chair if I write I at the top. Okay? Okay, so now I want to prove that phi I down, I is down, is a set of linearly independent vectors. So here I'm writing the linear combination in this way. Okay. So here, because here, this is an element in V star star B, which And this symbol with this bracket here means that I take an element of V star star B and apply it to an element in V star B. Okay. Okay. Here I use the definition. Phi EI applied to L is L applied to EI. So this is true by definition. And so here I have the right linear combination. Okay. Okay. Now, this equality, look what we have written. We have alpha I L E I. What is this? This is an element of V star B. Okay. And it is applied to V. Okay. Let us check if now it works. And this is equal for every V. Okay. And this is equal to 0. So let me check if I'm doing well or if there is another mistake here. No, there is something which is not true, because we have already, no, this morning I didn't wake up in the right way. So I will repeat for you everything, this part. Okay. I was mixing the index at the beginning, and since then I was totally wrong. Okay, so let us repeat slowly this. But let us try to use my mistake in order, everything was caused by the wrong localization of the index at the beginning. Okay, so let us use this series of mistakes in writing my formulas in order to make clear how powerful the method we have is. So, phi EI is a set of vectors in VP. Phi EI is a set of vectors in V star star V. Okay. And we want to prove that this is linear independent. So I think that now we are converging to the right result. Alpha I phi EI is equal to 0. This 0 here, this formula is becoming very crowded. This 0 is an element. I try to move this down. Okay, very difficult to do. Okay. So Let's do this way. Alpha I phi ei is equal to 0. And this 0 is what is the 0 in V star star B. Okay? And we want to prove that all alphas are 0. Okay? So what I do, I apply this element in V star star B to every L in V star B. And what I get is a real number. You see, I placed the index in the wrong position at the beginning, and this was the cause of a series of a chain of mistakes, which now we are solving simply because we recognized, and the index has to be up, otherwise we will keep doing wrong things. Okay, so this is an element in V star star B. I apply it to every element in V star B. So for every element in V star B, this is equal to 0. And this is the real number. Now I think that I'm writing the right formula. You must be very careful in these things, but I will teach you a mnemonic rule for writing always the correct formula at the end of this reasoning. Okay, so for every L, this is a real number. So I was wrong. There was a chain reaction, and this is obviously a real number. Okay, and this is what I wrote here at the end. Okay, now we are there. So this is true, but I don't repeat it several times. Okay, so for every L, you see, it is very easy at the end of the story. L alpha I ei is equal to 0. And this is a real number. Okay? So now I have alpha I ei, a linear combination of the vector of the vectors in the basis, which are such that for every L, this is equal to 0. Okay? So in particular, I can choose Lj. What is Lj? It takes a vector and it maps to this vector its jth component in the chosen basis. You remember? So this is equal to alpha j. So for every L, we have this. In particular, for every j, we have this. And this is 0. So at the end, we have proven that for every j, alpha j is 0. Okay, as I was doing some wrong, telling you some wrong statements, let us repeat once more this. Okay? starting from here. Okay, so we have, by the way, okay, let us tell this. You could write a symbol like this for meaning the duality in VB. This is a symbol which simply means L applied to V. So this is not an inner product for the moment. Okay. Why this notation is meaningful? Because here you can have L fixed and V variable. And in this case, you have L of V okay, the linear map which maps every vector V into real number, or you can block, you can fix L, and you can vary V sorry, the other way around. You can fix V and you can vary L, and in this case, you consider an element in the dual of V star. When V is fixed and L is variable, this can be regarded as an element of V star star V. Okay. So this is a way you can pivot with a fixed V and you vary L, and you can fix L and you vary V. Okay. And in this way, you get all possibilities in the duality. So this notation makes evident that the double dual of VB is the same vector space as VB. It is isomorphic to VB. But how to see this in detail? Technically, we said, okay, for every, let us repeat this from the very beginning. So I hope that now you will follow the reasoning another time, and there is no misleading notation leading to mistakes. So you get V, for every V belonging to VB, you are building phi of V as an element of the double star B. How? An element in double star VB is a linear map defined on V star B. Okay, so phi V, the image of the vector V in VB under phi must be applied to L to get a real number where L belongs to V star B. Okay. Now, by definition, this is the definition. Phi V applied to L is L applied to V. So when in this formula, or in this formula, you block, you fix L, V, and you vary L, you are considering a linear map on the set of V, in the set V star B, in the dual of VB. Okay. Now, this map, phi V, is linear, and I have proven this in these lines. So actually, phi maps elements in VB in elements of V star B. Okay. Then, in order, I told you that we already know that the dimension of V star B is equal to the dimension of V star B, which is equal to the dimension of VB. Okay. So we know that in V star B, we have a basis made exactly by the same number of vectors as we find in the basis of VB. Okay. So now I will find a basis of V star B. How? Considering phi of EI, the set phi of EI, and the index is down. Okay. So in order to keep this presentation ordered, you need to remember that EI is a vector in the basis of VB. So it is a set of linearly independent vectors. By definition, a set of linearly independent vectors is something such that every linear combination leading to 0, to the vector 0, is possible only when the coefficients are all 0. So to prove that phi EI is a set of linearly independent vectors, we must prove that if we have this combination equal to 0, all alpha i's are equal to 0. And how we do it? This is an element of V star B. So for every L in V star B, this equality is verified. So this B dual vector applied to a dual vector has to be 0 for every L. Okay. Then I apply the definition phi EI applied to L is L applied to EI. And this has to be equal to 0 for every L. Then L is a linear map. So alpha i's can go inside. Okay. So what we have proven that for every L, L applied to alpha I EI is equal to 0. Now I use EI, LJ, LJ we have also called EI, EJ at the top, but it is better to avoid for a while this. So these are the same name, different names for the same object. So as this is equal to 0 for every L, this is equal to 0 also for each particular Lj. Lj is mapping the vector alpha j ei into the jth coefficient. So this is exactly one of these. Which one? The jth. And so we prove that for every j, alpha j is equal to 0. So we can conclude that phi ei is a basis for V star star B. Okay, so now on, we will confuse EJ, EI with phi EI, and we will not talk anymore about V star star B, because V star star B is confused with VB. Okay. Okay, so let us do this way. I now repeated in the best possible way what I had to tell you in this context. However, you should learn also out of my mistakes. Placing this index in the wrong position caused me a series of mistakes, one after the other, and every formula which I had written was wrong. Why? Because after having written EI at the top instead of writing EI at the bottom, I forgot to be wrong at the beginning, and I was treating a vector as a covector, and so this caused me a series of mistakes, one after the other. So the localization, the placement of indices in our notation is essential, and I think that being able to place the indices in the right way and to give a meaning, okay, this is very important, to give a meaning to the placement of indices, in particular up and down, helps in detecting mistakes in the formulas. So it is a self-correcting notation. We are using a self-correcting notation. Okay. Now, let's go to CAB, VAVB. You remember, we have written F transpose F, we have called it C, And we said that the deformation observed in a deformable body locally so this is small. So we are considering the Taylor expansion. We have a central point x0, and the deformation is fully described by f equal gradient of key in x0. You remember, we started doing this, okay? So we had a bigger body, the placement to the actual configuration key, and then we zoomed in a region having dimension epsilon, and in this region we said that key of x is equal to key of x0 plus grad key calculated in x0 times x minus x0 plus, and we decided for the moment to neglect infinitesimals of higher order. So we wrote key x minus key x0 nearly equal to f calculated in x0 times x minus x0. So we introduce a linear map. So now you can try to understand why we are studying so heavily linear maps. But what we did, f maps vectors VB into vectors V small. Why? Because this is a displacement, and this is a vector of material particles. You know, before doing the next abstraction and before writing more about tensors, I want to recall you the motivations for which we are suffering in this way, introducing these mathematical abstract concepts. Okay? Then we introduced the inner product of the vector V and the vector W in the reference configuration. We considered FW, FV in the actual configuration. And we said the inner product WV in VB is changed in the inner product FW FV in the actual configuration V small. Okay. Then, if you remember, we introduced the transposed of F. So we wrote FW FV in VS. We wrote like W F transpose F V in VB. Okay. And we said that deformation is measured by the change of inner product induced by F transpose F in formula star. Okay. Okay, now if you want a measure of deformation which is equal to 0 when no deformation occurs, then you define G equal 1/2 F transpose F minus identity. Because F transpose F is equal to the identity when this map is rigid. So the angle between V and W and their length remain unchanged if and only if F transpose F minus identity is equal to 0. If instead of considering making this choice, you accept that no deformation means that the measure of deformation is equal to identity, then you can use F transpose F, which is usually called also C. This can be a measure of deformation when C is equal to identity, then no deformation occurs. Okay. So I think that this point is clear. Okay. So what is doing F transpose F? So you take a vector here, you calculate FV, then you apply F transposed, and you get another vector, F transposed FV. So you have V, it becomes F of V, applying F, then you apply another time F transposed, and you get F transposed F of V. Okay. So deformation is a physical quantity which is described by a linear map from VB into VB. Okay, now historically, as I told you, I think that Piola understood this being the first. in the literature, this is said to have been understood by Green. In this context, who did it is not relevant. C is a map from VB into VB, and this linear map describes deformation. C is the mathematical object describing deformation. Now, everybody here should have followed the class in physics first year. So I'm sure that you heard this story. I consider the mass m of a material particle, or I consider the temperature of a body. The mass is a scalar. You change observer, and the mass is not changing. You change the observer and the temperature is not changing. So temperature is a scalar. So there are physical quantities that are described by scalars. That is, real numbers. Okay. Then I'm sure that in physics, they told you that there are new and more complicated quantities described by vectors. I'm sure that they told you that there are some quantities, for instance, displacements, for which the intensity, or if you like, the length, is not enough. They tell you, if I move 1 kilometer from here, I'm not telling you where I am at the end. Why? Because I must tell you also the direction in which I am traveling. Okay? So there are some physical quantities which need more complex mathematical objects for being described, and displacements are an example of this. You need to give an intensity and a direction for describing these more complicated quantities. Okay? Now, thanks to Cartesian coordinates, if you introduce in three-dimensional spaces, if you introduce a Cartesian reference, then three numbers not this way, better not to do this way. These three numbers, the components of your vector in the Cartesian system of coordinates, give you the required specifications for describing a vector. Okay. Now, the system of coordinates is useful. Why? Because you can describe direction with a unit vector. So you give the three coordinates of, let's call the unit vector E. So you give E1, E2, E3. You write that E1 squared plus E2 squared plus E3 squared is equal to 1. And you have precisely said what is a direction. However, when you change the coordinate system, the components of a vector change. So we have also some drawbacks in introducing the coordinate system. However, you know, we have written, and what we have done up to now is, I think, now clearer. If I have a vector V, I can write it as a linear combination of one basis. I can write it as another linear combination in another basis. Okay. I'm lazy and I'm not writing prime there now on, you remember? And we have studied contravariance of BI when the basis changes. Okay. So when we are dealing with quantities described by vectors, we must learn more mathematics. Scalar quantities are very well described with real numbers. Instead, vector quantities require components, and you must learn how to study the change of components when the basis is changed. So you find in a book like Feynman, you find a statement like a vector is a set of components changing in a contravariant way when the basis is changed. So a vector is not a set of components. A vector V is what? When you fix the basis EI, it is the components VI. When you have E prime J prime, the components are Vj prime. And if you have E second J second, the components are Vj second, and so on. And these components are changing in a contravariant way. So you have the matrix of transformation here, and the components are changing in a contravariant way. Okay. Deformation is new, is newer. It is a more complex physical quantity than displacement. Why? Because deformation is described by a linear map, F transpose F, of a vector space into itself. In order to describe deformation, you need to introduce a linear map. So now we must study how linear maps change when we change the basis. So we have now a strong motivation for continuing our reasoning. Up to now, we understood how vectors are changing. Okay? And we also understood that there are, in reality, two kinds of vectors. You have vectors and covectors. We gave an example of covector. A force is a covector. Why? Because F dot V is a linear map in the set of velocities. The definition of power gives you naturally a linear map from the space of velocity into real numbers. So you have displacements which are vectors, and forces, which are covectors. Okay. Now, as we want to study deformation, we are facing another difficulty. We must deal with a more complicated mathematical object, a linear map. Okay, so I think that we can rest 10 minutes because today we go up to Alessandro, you can stop recording. Alessandro. Okay, he's not here. So I suggest you, Ivan, possiamo staccare la registrazione?
Sì, scusate, ero al telefono, mi hanno telefonato. Interrompo.
Stacchi un attimo la registrazione.